third part of ER model series. So we in the earlier lectures we have seen how we have the various components of the ER model and the constraints, the relationship sets. So we also learned about the mapping and the cardinality constraints. So we are going to look into this and as far as I remember, there were two types of constraints on the relationship sets. So if we have this relationship set, so on relationship set, there were two constraints as I earlier told. So the very first was the participation constant and the second one is the mapping constraint or the cardinality constraint. So we are going to look into these two from some examples. I'm going to explain about these two. So just to summarize, revise the previous concepts, participation constraints can be either it would be total participation or it would be partial participation. Like if for two entity sets, if all the entities of the entity sets are mapped onto the relationship, then it is a total participation, and if not, then it is a partial participation. We told learned about. Okay, so this is the thing, and then we have the mapping constraint as the cardinality constraint. So we already seen that we have one to one mapping, one to many mapping, many to one mapping, many to many mapping, and based on that we determine the key for the relationships. Okay, so let's have some examples based on that. So let's see, there is a entity relationship model diagram E1. There is a relationship set R. There is one more entity set E3. Okay, and then we have E2. Okay, for E3 we have the candidate key C. For E2 we have B as the candidate key, and for E1 we have A as the candidate key. Now, this R is actually map. It's a one-to-one mapping for all. It means that one entity of R E1 is related to one entity of E2, and so as for E3. So since it is one-to-one mapping, like one-to-one is for binary, but for all these relationships we have one-to-one mapping. So definitely A, B, C will come. And since we have one entity of E1 mapped to E2, one entity of E2, and one entity of E2 is mapped to one entity of E3, hence we have the candidate key as A, B, C. All these three are the candidate key for R. Okay, so this is one determination for the candidate key for the relationship set. Okay, so this is the set of candidate key for the relationship. Why? We already seen that when we have a binary relationship, E1 map to E3, and it is a one-to-one mapping, then both the key attributes are separately treated as the candidate key. Okay, so it is just an extension of one-to-one binary relationship model. Okay, let's come to the second example that we are going to see, and in this we have, let's suppose this is an entity set E1. We have a relationship set R. We have another entity set called E2. Let's say E3, and there it is E2. Okay, and here we have the attribute, key attribute as A. Here we have the key attribute as B, and here we have the key attribute as C. So, and please note that this is a many to many mapping. I mean, many to many mapping we had already seen for binary relationship. So this is a ternary relationship and it is a many to many mapping. And when it is a many to many mapping, then we have one or more entities of A is related to one or more entities of B, and that same goes for E3 too. So we have this whole as the candidate key, right? So if it is asked what is the candidate key for the relationship R, then it will be definitely A, B, C as a composite key, okay? Because we can't use A or B as a single candidate key because it won't be unique. Like we already seen that A1 may be related to B1 and A1 may be related to B2 as well. So we can't treat A as the candidate key. Same goes for B and C. So together they compose as a candidate key. Okay. Let's see one more example based on that, where we have 1M mapping. So this is our E1, and there is a relationship set that is R. Then we have this as E3, and we have one relationship set, entity set as E1. Here our candidate key is A. Here we have the candidate key, sorry, this is E1, this is E2. We have the candidate key as B, and here we have the candidate key as C. Now, the mapping would be this is one, many, many. So we have R, A, B, C, and A is from E1, it is one to many mapping. Okay, so one entity is related to many entity of E1 and E3. Like A1 is related to B2, B1. A1 is related to B1, C1, C2, like so. So there will be repetition of A1 here, okay? But there won't be repetition of B1 or B2. Like B1 will be 1, B2 will be 1, okay? In short, it is a 1 to M mapping. And when it is a 1 to M mapping, then definitely the many part key, candidate key, will be treated as the candidate key for the relationship. Okay. So either B or C will be the candidate key, right? So we can say that, okay. So let's see if we have, we will treat it as an example. Just a second. Right. So, okay. So if for even like we have A1, okay, we have A1 is mapped to B1, A1 is mapped to B2, and A1 is mapped to B3, okay, and then we have A2 mapped to B2, like so, okay. So this is one to many mapping. Then we have A1 can be mapped to C1 and C2, right? And A1 can be mapped to C3 as well. A2 can be mapped to C4, like so. Like this is the basic configuration, right? So here you see we have this repetition for A1, okay? Maybe the exact relationship set cannot be possible to implement, but this can be the situation that A1 is mapped. But here you see that if we treat B as the key, then definitely this B1 may come one time, but B2 is coming two times, right? So this can be the mapping here. So not exactly we can say that it is one to one, one to m mapping, because here we have three entity set. We don't have two entity set. So in that way we can have this BC entirely as the candidate key. If we see BC, then definitely it is a one to m mapping and m part is coming as the key. So if we say the candidate key here, so the candidate key could be BC as a whole. Okay, because we are not taking as B, because A is not mapped only to B, it is mapped to C as well. So we can't take it like B can be the candidate key or C can be, because if we are taking 1 is to M mapping, then M part will be coming as the candidate key. So exact relationship set may not be possible to implement in this way. Okay. Uh, let's see another example. Okay, so there is something like there is a question of the ER diagram, and we have to pick up the correct ER diagram for the given specification. So the specification here, the question specification here is each kid likes zero or more candies, and each candies liked by at most at most one kid. At most means 0 or 1. Now, at most and exactly are two different things, we'll see. But let's now here concentrate on the examples. So the options. So we have this kid as one entity set, and this, you remember, and this is a relationship set, and this is the likes, and this is for the candies. Okay. So, when we talked about the total and partial participation, right? So, we had something called double arrow and single arrow. We talked about the double arrow and single arrow, right? So, what does this signifies? This signifies total participation, and this signifies partial participation. What is total participation and what is partial participation? Total participation means every entity of the skit set will come into this like. Okay, all the kids will come. This means that every kid has to like one candy, right? But not all candies are liked by every kid. Okay, let's see the second one. This is kid. Then we have this, and yeah, this arrow indicates 1 to M. Like one kid can like zero or more candies, but one candy would be liked by zero or more kids. Like candies can be liked by the kid or cannot be liked by the kid. Okay. So, okay, we will be explaining this example entirely, but first let me write the options. What are the options? This is single partial participation. This is total participation, and this is the candy set, entity set. Okay, this is also 1 to M, but here it is total participation. Okay, then we have the third option as there is a kid set. Then we have this total participation, likes. Then here we have many to one, and this is the candy set. Like two or more kids can like the same candy. Okay, and the fourth one is kid. Then we have this like set, then we have this candy. Okay, so this will be also M to 1, but the this is total participation, and here this is total participation. Now it's a bit of confusing because we are dealing with cardinality and participation at the same time, but I'll explain everything. Okay, so let's come to our statement. Our statement was each kid likes zero or more candies, and each candy is liked by at most one, or at most one kid. That means each candy is liked by zero kid or one kid. Okay, that means we don't need to have a total participation here, right? If each candy is liked by zero kid, then we don't need the total participation. So here partial. Okay, so here we can have the partial participation for the candy set. For the kid set, each kid likes zero or more candies. So here also we don't need the total participation. We can have the partial participation here. Because kids may like candy or may not like candy. Okay, zero or more candy means kids may like candy or may not like candy. So we can have the partial participation. So we can search for the partial participation here. So there is no option like so where we can have the partial participation. There is total, partial, total. So obviously it will be none of these for this question. Okay, this will be none of this for this question. Right now, let's change the question a little bit, and instead, okay, let's change the question a little bit, and instead we can have here modify the question as each candy liked by, instead of utmost, if we have exactly one kid, each candy liked by exactly one kid. Now it won't be partial enough. Okay, so if it is exactly one kid, so all the candies needs to be participated. So this will be total participation at the candy's end. Okay, so there should be total participation here. Okay, now we have to check for the cardinality. Okay, one to one mapping or many to one mapping or one to m mapping. So each kid like zero or more candies. Each kid may like zero or more candy. More candies means, for example, if there is a kid K1, K1 can like C1, K1 can like C2 as well. So one candy, one to many. Like one kid can like many candies. Okay, so it is 1 is to m. So where we can find 1 is to m? This is 1 is to m. And at the candies, I already mentioned there should be total participation. So our answer B is the correct answer. If it is for exactly. Okay, so in this way we can have many options and we can pick up from the options. So this was all about the constraints on the relationship sets. We have two constraints. First is the participation constraint, okay, and the second is the cardinality constraints. So both these constraints can act together and we have to pick up the right option for that. So very important point to note here that for the cardinality constraint we can have 1 is to 1 mapping, 1 is to many mapping, many is to 1 mapping, all. Okay, and these relationship sets can combine into same entity set. Okay, this is an important point because next we are going to discuss about how we can convert our ER model into RDBMS table. Okay, this is the third step as I told earlier in the steps for designing the ER model. So it's the third step. First we get the requirements, we draw the ER diagram for that, and then we convert that ER diagram into RDBMS table. So if it is 1 is to 1 mapping, 1 is to M mapping, and m is to 1 mapping, then the relationship sets can be combined into a single entity set. But if we have the second note, if we have m is to n relationship set, m is to n relationship set must maintain into separate RDBMS table. Okay, here not allowed to merge. This thing needs to be maintained. So that is why we have learned about these participation constant and cardinality constant. So we are going to look into this in the next lecture. Till then, goodbye. Have a nice day.